Take a second problem involving support settlement. Same B problem involving a support settlement. Let us take this example. Take a B. Suppose B and C settles down by into E by EI and OE by EI. So let us take this problem. Analyze the beam, continuous beam shown in the figure. When the support, mixed support as well as right-hand support settles down by 2000 by EI and 1000 EI. Again, to solve this problem, we have to follow the same steps which have been given there on the right-hand side. So let us follow that. The first step, we have to identify the independent forces to be determined at the ends of all the members. So that is called element coordinates. So here in this problem there are two elements, AB and BC, or two members, AB and BC. So I told you generally we select the moments at the ends of the member as the unknown. So the coordinate direction we take clockwise as positive, like this. So here for AB, two ends, A and B, the coordinates are 1 and 2. For BC, it is 3 and 4. So this is element coordinates that I have selected. So we have to determine during our analysis the member and forces corresponding to these coordinates. That is PM1, PM2, PM3 and PM4. This is what we have to determine during our analysis, final analysis. That's what this first step. Identify independent forces at the ends of elements or members with the element coordinates. That is this. And identify what are the end forces to be determined. Then second step, you have to find the degree of static indeterminacy and make the structure determinate. Here it is a beam, so the static indeterminacy is given by 3m plus or minus 3j, where m is number of members, that is 2, and r is number of support reactions, that is 5. 3 here at fixed end, 1 at roller, total 5, minus j is number of joints, which is 3, that is 3 into 3. So the degree of indeterminacy is 6 plus 5, 11, minus 9, it is 2. And the degree of external indeterminacy is r minus 3, that is 5 minus 3, 2, and internal indeterminacy is 0. That means, so this beam structure, whatever is given for analysis, is internally determinate and externally it is indeterminate to the degree 2. That means 2 of the external reactions has to be chosen as redundant. Those reactions, if we remove it, then the structure becomes determinate. That's what I have to do. Now what I will do is, as we did in the previous problem, we remove the moment at this end A as well as another, we introduce an internal hinge at B. That means we impose a condition that is external condition, that is moment at B, we make it 0. So make the structure determinate by introducing or by removing moments at A and B as below. So that means I'll make this here hinge, thereby I removed the moment. So this is that I have removed, and of course these are all the element coordinates. We use the notation that 1 star, 2 star and 3 stars, element coordinates. This is actual forces we use like this. And here, this is first coordinate, that is the moment I have removed at A, and at B also I will remove moment by introducing a hinge, internal hinge like this. So that means I have removed moment here. So the directions of those moments removed are like this, 2 coordinates. This is that. So this is basic determinate structure, and redundance. That is R. Redundance R. So that is R is redundant forces removed, or is R1 and R2 corresponding to these coordinates. That is step 2. Find the degree of static indeterminacy, which is 2, and make the structure determinate by selecting redundants with coordinates. I have selected the redundant forces as the moments at the supports in this fashion. So that is second step. Then third step, you have to determine the unassembled element member stiffness matrix. That is unassembled flexibility matrix. FM. That's what I have to do. So for this, I have to determine the flexibility matrix for the individual member. There are 2 members. For those 2 members, individually you have to determine the flexibility matrix. So generally we choose the moments at the ends of the member as the independent forces. So therefore choosing that the flexibility matrix is given by L by EI into 2 minus L by 6 EI into 2 minus 1 minus 1. So that's the flexibility matrix for a B member, choosing the end moments as the independent force. So with that, which we have already derived, that's what I have given here also. L by 6 EI, 2 minus 1 minus 1, 2. Where L is the length of the member. I am taking the first member. For this first member, this is second member. For first member, length is 10 meters. EI is EI itself, so it is 10 by 6 EI, 2 minus 1, 2. Or it is 5 by 3 ei 2 minus 1, 2. Similarly, Xn2, that is also same length, 10 meters. A is also same, so the flexibility matrix will be same, 5 by 3 ei 2 minus 1, 2. Therefore, the unassembled flexibility matrix of the structure will be, I have to combine these two element flexibility matrix and put it in the diagram. So, diagonal. So that is 5 by 3 ei, I will take it outside. Here, for first element, 2 minus 1, 2. For the next element, it is 0, 0. Next, for second element, it is 2 minus 1, 2. So this is the unassembled flexibility matrix of the entire structure. Unassembled flexibility matrix. So that is the third step. I have completed the third step. Next, fourth step, we have to develop a transformation matrix. So transformation matrix. So this we are developing by applying unit load one at a time along the global coordinates, that is along the redundant coordinates, and evaluate the corresponding forces along the element coordinates. So first I have to apply unit load 1 along the global coordinate, that is this redundant coordinate unit load, and determine what are the forces corresponding to these element coordinates. So that is force here, here. So when I apply a unit moment here in the basic determinant structure, so this becomes independent, this becomes independent. The moment I introduce internal hinge, so this can be treated as independent, simply supported beam. So here the reaction, it will be 1 by 10. Here it will be equivalent opposite 1 by 10. Therefore, moment here, this will be 1 in this direction. So here, moment will be 1 by 10 into 10, that is 1 here, so that will cancel, so it is 0. Here also it is 0, 0. So the first column of the T matrix will be this, it is same as this element coordinate direction. So it is 1, 0, 0, 0. So next, I have to apply unit moment or unit load, not moment, it is unit load. I have to apply along the coordinate 2, that is here. I have to apply unit moment R2 equals 1. R2 equals 1, and similarly I have to determine what are the moments developed along corresponding to these element coordinates. So here, as you hear, this becomes independent, simply supported beam. So here the reaction will be 1 by 10 like this. So here also reaction will be 1 by 10 like this. So here, reaction will be opposite direction. It is 1 by 10 plus 1 by 10. So this gives the moment to this fashion. So here, moment is 0. Here, moment is in the same direction. It is 1. Here, it is 1. Here, it is again 0. So these are the moments developed. Therefore, second column of this transformation matrix will be, this is 0, here it is minus 1 because it is in the anti-clockwise direction. Here we have taken positive direction, so here clockwise as positive, here it is anti-clockwise, so it is -1, here it is +1, here it is 0. Therefore, combining these two, we get the force transformation matrix as 1, 0, 0, 0, 0, -1, 1, 0. So it is a 4/2 matrix. So this transformation matrix we get by applying unit load along the redundant direction successively and evaluating the forces corresponding to these element coordinates in this fashion. So that we will get as transformation matrix. That is this develop force transformation matrix T by finding element member and forces. That's what I have done. Element member and forces I determined due to unit applied load along the redundance. Here R1 equals 1, R2 equals 1. Successively I applied, I got the moment. Because this structure is made determinate by introducing internal heat, each span will become independent simply supported. By applying the equations of this result, I got these forces. So that is a simple procedure. Next, fifth step, you have to find the structure flexibility matrix, that is Fs. So this Fs you can determine by the contractility principle which we derived, that Fs is given by Tt Fm T. So if you apply this formula, so you can evaluate that Fs is equal to Tt. That is transpose of this, it is 1, 0, 0, 0, 0, -1, 1, 0. Then Fm is this 5/3ei into this 2 -1 -1 2 0 0 0 0 0 0. Then again here 2 -1 -1 2. That is this Fm into T. T is 1 0 0 0 0 -1 1 0. So that is Tt into Fm into T. So we have to first multiply these two. That this is 4/4, this is 4/2. Column here equal to row. The resulting matrix will be a 4/2 matrix. This 4/2 matrix is obtained by multiplying each of these rows with the column. That is 2 into 1, 2 -1 0 0. It will be 2. And next 2 0 -1 1. It is +1. Then -1 1 -1. Then it is 0 -1. Then this -2. Next is 0. This -2 -1 or 2. Sorry. This is -1. This is -2. This is 0. This is 2. This is 0. This is -1. This we have 5/3ei. Then this of course remains same. 0 0 0 -1 1 0. So now these two have multiplied. So this is 2/4. This is 4/2 column here equals row. resulting matrix will be a 2 by 2 matrix. That is nothing but our Fs. So this is 5 by 3 bi. So this is 1 into 2, because 0 is 2, then 1, then 0 plus 1, 0 plus 2 plus 2, it is 4. Plus 2 plus 2, 4. So this is my Fs. So I can determine Fs inverse also here itself. So that is nothing but VEI by 5 into determinant of this, it is 1 by 7. Determinant of this is 8 minus 1, 7. Then cofactor of this, it is 4. Then minus 1, then minus 1, 2. So this is the inverse of flexibility matrix. So I have determined this. That inverse actually it is here, it is told. So I determined here itself. Just below that, after generating structure flexibility matrix, inverse also you can determine there itself. Then 6 step, that is this. Load matrix we have to determine. Here it is load and displacement matrices that we will get. So here actually the loads, now I am considering, actually loads on the structure are nothing but the equivalent joint loads, equivalent member angular forces corresponding to element coordinates I have to determine. So that I will determine first PM is nothing but equivalent joint load. So this first, I will take this number as fixed. Here it is fixed, so it is 240. So here fixed end moment will be 2WL by 8. That is 240 into this L is 10 meters. 240 into 10 divided by 8, that will be 300. Here this will be 300. So next, BC member, this is AB. Then BC member, it is subjected to 120 kilonewton load. So the fixed end actions, it is 120 into this also 10 meters, 120 into 10 divided by 8, that is 150. This also 150. These are the fixed end actions due to given loading. So in addition to this, settlement is also given. Due to that settlement also, you have to work out the fixed end moment. So here it has been given that B has settled down by 2000 by VI. 2000 by VI. So when it settles down, AB, when this has settled down, so that means there must be a force in that direction in the B. So to keep this in equilibrium, there must be equal and opposite force like this. So to keep this in equilibrium, there must be a force here in this direction. This is giving a clockwise moment. That means this is again it is not in equilibrium. To keep it in equilibrium, there must be a force here, here in the opposite direction. And these are nothing but our fixed end moments. So this fixed end moment value is 6 EI. EI is EI itself. Delta is 2000 by EI. 6 EI delta divided by L square. L is 10 meters. So L square is 10 into 10, 100. So if you simplify this, you will get 20 into 6, it is 120 by VI. Here also 120 by VI. both in anti-clockwise direction. That is due to settlement of support B and the fixed end moments. Because of that settlement, what are the fixed end moments in member AB? Next, for BC on similar lines, so B has come down by 2000 and C also has come down by 1000. So this is that BC. The fixed end moment due to that, you have to find out. This has come down by 1000 by EI. This has come down from the original position. This has come down by 2000 by EI. So next, the BC member has come down by 2000 by EI minus 1000 by EI, that is 1000 by EI only. So because of this, there will be fixed end moment. Since it is coming down here like this, there must be a force. Here, there must be a force to keep it in equilibrium. But again, this is not in equilibrium because this gives rise to a moment in anti-clockwise direction. To keep it in equilibrium, there must be a moment in the clockwise direction. And that moment, as I did here, its value will be 6 EI delta by L square. Now here, delta will be 1000 by EI, the net deflection. Therefore, the force here, it will be 6 EI, delta is 1000 by EI, 6 EI delta divided by L square, that is 10 square. So this value will be 60 by EI. So here also it is 60 by EI. But it is in the clockwise direction. Here it is anti-clockwise, here it is clockwise. That's what you have to determine before finding the member load, equivalent joint load. Now the equivalent joint load is these loads, moments, whatever we got due to applied load as well as due to the settlement. This will only change from the previous example. That is, whenever there is a settlement, due to that settlement also you have to find the fixed end action, and that you have to add it. So here, the net moment along element coordinate direction 1, it will be 300. Here it is at end A. Here it is at 120 by EI. That's in the same clockwise direction. So 300. Oh, this is not 120 by EI. This EI also gets cancelled. So it will be just 120. So same thing here also. EI will get cancelled. So it will be just 60 by EI. So here, the along 1, the total moment will be 300 plus 120. There is no EI. That EI gets cancelled. So 300 plus 120. It is in the same anti-clockwise direction, so it is 420. So here it is, or the B is different. So at A you have 420. So that direction is in the anti-clockwise direction, 420. That I have to reverse it. So it is clockwise 420. So this PM matrix, whatever I have to generate, is the opposite, it is in the opposite direction. So that the PM along the element coordinates. So it is at A along 1, it is 300 anti-clockwise, here 120, 420, but I have to reverse it the direction. So that will be 420, 320 plus 300 plus 120, 420, which was acting in anti-clockwise direction, that direction I have to reverse it. So clockwise direction, so plus 420. Similarly, along the coordinate 2, that is at B, it is 300 here, at B, it is 150, 300, 150. So this is clockwise, this is anti-clockwise. So 300 plus minus 150. No, not 350. So this is here in this direction, that is 2, that is 300. It's only 300 you got. Then here it is 300. Then in this direction it will be 120. 300, 120. 300 is clockwise, 120 anti-clockwise. So 300 minus 120, it becomes 180. 180 in the clockwise direction. That direction I have to reverse it. So it is minus 180. Then along 3 means it is this. Here it is 150. Then here it is 60 like this. So 150 minus 60, that is 90. 90 in the clockwise, anti-clockwise direction, that to be reversed. So this is plus 90. Then along 4th direction, it is 150 here. So here it is 60. 150 plus 60, 210. So direction I have to reverse. So it is minus 210. So along 4 direction, these are the moments. This is my PM due to external loading. Both settlement as well as given loading I have worked out. That is PM I have worked out. Then I have to use this formula TT FM into PM for calculating DL. That's all. That's the last step for calculating the load. Displacement DL. Then finally you can find out the unknown forces, that is redundance. So 6th step over, then 6th step which is continued again, because I have to calculate this. Therefore, dl is equal to dt into Fn into Pm. Only here to calculate Pm, that is the load, I have to do this exercise. I have to assume each end to be fixed for the given loading as well as settlement. This is the picture. I have to work out the end moments, then add all those things. Reverse its sign. That's why I made it. Here, though I am getting 300, 150, 450. 300, 450, not 420. 450 I am getting. 300 plus 125, 420. So this is due to given load, this is due to settlement. It is 420. The direction is clockwise. I have to reverse the direction. This is anti-clockwise, 420. I have to reverse it direction. That means 420 clockwise. 420 clockwise means it is positive because element coordinate I have taken as clockwise positive. So like that, I have ordered that. To substitute all those values, Tt is given by this 1, 0, 0, 0, minus 1, 1, 0, that is Tt, or not that Tt. Tt is, I have to change it into, throw into column, that is 1, 0, 1, 0, 0, 0, 0, minus 1, 1. This is that T. T is this. T transpose is this into Fn. Fn is 5 by 3ei, and of course this is 2, 1, minus 1, minus 1, 2, 0, 0, then 0, 0, 2 minus 1, minus 1, 2. That is Fn into PM matrix. PM matrix, just now I calculated, that is 420, then minus 180, then 90, then minus 210. So I have to multiply these two because first it is 4 by 4, this is 4 by 1. So if I multiply, I will get a 4 by 1 matrix. So this is 2 by 4. This and this, if I multiply, this becomes a 2 by 1 matrix. That is my dn. dn is given by, I'll straight away take it. That dn is given by, I've calculated di 1700, this is 90, that is 2 by 1. This is that dn, that is that 6 step. You have to work out whatever dn is. Then last step, that is 7th step, you have to find the redundant source. To find R, that is corresponding to global coordinate R1, R2. What is that moment value? You can find out from here. So for that, we have the formula. R is given by Fs into dr corresponding to redundant. So that is nothing but Fs. This dr is dl minus dj. So dl is imposed external load. Here both the imposed settlements at B 2000 by VL, at C 1000 by EL. There are vertical settlements and not the rotatory displacement. It is only vertical translated displacement and not rotated type of displacement. So this dj, though there is a settlement is given, here this dj is corresponding to redundant selected. Redundant selected is moment. Due to that moment, so that is rotation, there should have been occurred there at those points, that is external displacements at joints. They are purely translation and not rotating one. So therefore this dj will be 0. So that if you use it straight away, you can work out this R. R is given by this Fs inverse. Fs inverse we have determined there, that is 3ei by 75, not 75, 35. 7 into 5. 5 into 7, 35. 3ei by 35 into 4 minus 1 minus 1, 2. That is Fs inverse. dl just now have determined here. It is 1 over ei 1700 1950, that is minus dl. So it is minus because this is sorry. This equation is dj minus dl. dj minus dl. That's the equation. So it is minus dj is 0, dl is minus. So if you simplify, you will get the redundant forces as the final value 4 minus 415.7. This is minus 188.5 pound. So this is the redundant forces. So the moment you get redundant forces, so you can draw the Getty moment diagram as we have done previously. This is about analysis of beams due to settlement of support. Only change you have observed from usual analysis of beam is here, that is in the sixth step, wherein in addition to, by calculating PM, in addition to given external member load, you have to take the effect due to this settlement of support also, whatever the fixed action. And remembering that these settlements are not corresponding to redundance, because these settlements, there are vertical translations given. It is nothing to do with our redundant rotation, externally imposed condition or imposed settlement which has not been corresponding to the redundant. Redundant fusions are all purely moments. So if at all there is a rotation type of displacement is given there, then you could have used that directly in this final formula dj. If there was instead of vertical settlement of 2000 by EI, 1000 by EI, if they would have given this B, it rotates by a certain amount, some radians in the clockwise direction, if they would have given, then that would have been substituted here as dj. Clockwise rotation means positive, anti-clockwise rotation negative, that you could have substituted here and used it. That's the only change you have to incorporate whenever settlement is given. First you have to ascertain whether the given settlement is or maybe is pertaining to redundant direction or it is not pertaining to redundant direction. If it is not pertaining to redundant direction, then you have to go and find only the fixed end moment similar to external load, and that you have to take care in the PM calculation. If it is pertaining to redundance, then in this final calculation, you have to substitute that whatever amount of settlement is given straight away there, and that you have to use it in the computation of the dj minus dl, and accordingly R has to be worked out. This is the change which you have to consider during the analysis of beams. So with this, we have completed analysis of continuous beam, including this secondary effect of settlement of support as well as gravity loads. Next, we will take up analysis of stress.